Welcome to this video session. Today I will talk about the usage of AES in CBC mode. In particular, I'm going to talk about how to generate nonce-based IVs. Nonce means number used only once. Okay, and the fundamental problem with CBC mode is that usually we need an IV, an initialization vector, like this picture shows. During encryption, we need an IV, and of course, during decryption, we need the same IV as well. IV is there to help introduce randomization into our encryption process. As you can see, if the CBC mode is used with the AES, the number of bytes for the IV would be 16 bytes or 128 bits. So in many cases, that may be not necessary. For example, if the sender and the receiver are synchronized, meaning either the sender sends the message ID to the receiver, they can actually derive an IV from the message ID if we treat message ID as a nonce. So the idea is to not directly generate a random number. Instead of generating a random number, we will use something called nonce. Nonce is a number used only once, and to convert that nonce into an IV in a systematic way. So I will talk about it now. We have something called nonce, right? Number used only once. I want to be careful here. Only once is important. Okay. So what we, sorry for that. We have a number used only once, like here. What we do with that number, we encrypt that nonce, okay, using an encryption algorithm. Okay. For example, we use AES to encrypt the nonce. So we will send it to AES is going to take our nonce as input and encrypt this data for us. What is the output of AES? AES is going to give us a bunch of random bits. That random bits we will consider as an IV. Okay. So now the question is, what is the encryption key for the AES algorithm? Yeah. Okay. You probably know that we are using AES also here during the block cipher encryption. We do AES decryption during decryption, of course. So we need a key, and that key is usually better to keep it different from the key we use to encrypt. So we would need some kind of a let me call it nonce encryption key, NEC. Okay, so it is like this. So AES takes two inputs. One is the nonce, another is the NEC. So the question is, how do we get the NEC from? NEC is the nonce encryption key. So one idea is to use something called HKDF, which is hash-based key derivation function. Like usually we use a HMAC or something like that. Hash-based key derivation function that will derive a key for us. Okay, what it means is that in this case, we take the data encryption key, you know, the key that we are seeing here. This is the data encryption key, this part, key you see here, data encryption key. That data encryption key will be used to derive another key. So essentially, we do something like this. We take, how do we get NEC? NEC is nothing but HKDF of the data encryption key. Data encryption key or DEC. So now we have two keys. One is the data encryption key that is used to encrypt each block of our text, and then we have a nonce, which is just a message number or any number that is used only once. It need not be random, and it need not be secret at all. What we do though is that we send the nonce to the AES encryption block and use the NEC as an encryption key. The output from that process is going to be our initialization vector here. So here is the initialization vector, and this is what we get out from the nonce-based encryption process. We take a nonce, we take the NEC, the nonce encryption key, and we run it through AES to get the IV. Okay. Although CBC mode can be applied for other encryption algorithms, not just AES, but I am going to just make all my discussion around AES only. Okay. All right. So we have everything ready now to move on to the implementation details. This is the idea, right? Let me summarize it quickly. We have the traditional CBC mode. We want to avoid sending IV as part of the ciphertext, or we want to avoid storing the ciphertext IV as part of the ciphertext. So in that case, we want to generate IV in a systematic way. If both the decryption and encryption agree on the nonce, either by the protocol convention, message number 0, 1, 2, and so on, or the encryption process just sends the message ID, which may be much smaller than the IV itself. The IV, as I mentioned earlier, is 16 bytes for AES, which may be too much for some applications. Imagine this case where your plain text are all small, like just only 16 bytes of plain text. For every 16 bytes of plain text, you would need another 16 bytes of IV, which may be too much. Therefore, this idea is that you generate the IV during encryption. Of course, you generate the same IV during decryption using the same nonce during encryption and decryption process. When I say same nonce for only one message, okay? You never reuse nonce, of course, between multiple messages. In some standards, there is some discussion around using the same key, use the same key for deriving the IV, and also use the same key for encrypting individual blocks. But some books are actually not in favor of that. There are some attacks possible if the nonce itself is controlled by the attacker, then there may be some problems. So I'm not going into the details of how you can attack this system if you use the same nonce encryption key and the data encryption key. Okay, actually, even the NIST document that is explains the best practices for IV generation has two suggestions, right? One is based on generating a random number. FIPS approved means Federal Information Processing Standard approved in random number generator, which we saw in other videos. The other method is nonce-based counter method, like the one that I am talking currently. So these are the two recommended methods for generating unpredictable IVs for the CBC mode. What is interesting here is that they mention here you could use the same key for encryption of the plain text to a nonce encryption. That may not be always good. There are cases where this can be problematic. Okay, again, I'm not going into all the details of that chosen plain text attack possibility. But for our purpose, we will make a much stronger assumption that from the data encryption key, we will apply hash-based key derivation function to derive another key. So both the encryptor and the decryptor can actually generate IV whenever they need. Okay, that's the idea. So let's get into the code and talk about how we can use this scheme. All right, so I'm going to demonstrate to you now how to generate the IV from nonce. So I took a simple example, the same example we saw in my previous session, where we used the simple counter like 0, 1, 2, 3 as IV, which was not a good idea at all. We were able to find patterns in the plain text from the ciphertext. So you don't want to directly use the nonce as part of the CBC process. What you wanted to do is encrypt the nonce using another key, nonce encryption key, and I'm going to show the steps now. Let me start directly from the main. First step, as usual, is both the sender and the receiver agree upon the encryption key, right? Using a key exchange mechanism, whatnot. Symmetric key has to be established. That's the DEC part, right? The data encryption part. Of course, the same key will be used for decryption as well. Now, the interesting part is specific to nonce-based IV is that we need to generate a new key that will be used to encrypt the nonce. That's what I call it, nonce encryption key. I came up with this acronym NEC. Nonce encryption key may not be the best, but that's what I could come up with. What does NEC do? NEC is basically simple. It takes one argument, which is the initial key, that's the DEC, the data encryption key, and then it applies the hash-based key derivation function, which is an interesting cryptographic function. What it does is it derives one key from another key. That's what exactly we are doing here. We apply HMAC SHA algorithm. Salt is the text we will encrypt, quote unquote, encrypt using HMAC. You don't really encrypt in HMAC, but you can imagine salt is used to create uniqueness.
Okay, and then we have an optional info, which is additional data needed to identify, but these things are not necessarily secure. It's open, no worries about that, but you have to make sure it's unique. So both this encryption and decryption must use salt and info. Some implementations allow salt to be empty and info to be empty. That's fine, as long as you can make sure your nonce is unique and both the sender and the receiver are using the salt and info in a consistent way. Meaning, of course, if the sender uses a different salt and the receiver uses a different salt, then they will not get the same nonce encryption key. You will get into problems. So this is the standard key derivation function, which you can look it up in the internet standard books, okay, or the NIST guides and so on. Okay, once you have the neck, which is basically a key which can be used now to encrypt our nonce. So let me show you how that works. So we have a bunch of plain text. In my case, my plain text are stored in an array just for a demo purpose. And now I'm going to generate IV now. So what I'm going to do is I take my plain text ID as the I as index and the neck as another input, right? Neck is the nonce encryption key, which we just generated. How are we generating the IV? We use the simple technique here. If the message ID is 0, of course, the loop will not run. The nonce is bunch of zeros in this case, right? Because I have not done anything to nonce. And then we encrypt the nonce. Okay, how is encrypt nonce work? Encrypt nonce basically takes the nonce and the neck, the nonce encryption key, and encrypt using regular AES. Okay, now comes an important point I need to clarify. It's not possible to encrypt one block of text using AES in Java. Java doesn't allow you to use AES directly. You need to use AES in some cipher mode, for example, ECB and so on. I know ECB is not good. There are a lot of criticisms out there. That's true, and I agree. But in this case, remember, our goal is to encrypt one block of nonce, right? Nonce has bunch of zeros, only one block. It's perfectly fine to use ECB in that case because the nonce is supposed to be unique. It's something that is not going to repeat. Therefore, it doesn't matter whether we use ECB here or not. In fact, we can't use any other mode easily because all other modes would require an IV. So it's an interesting chicken and egg problem. So in order to generate an IV using nonce-based encryption model, we need to use AES directly. And the only option I could see is use it through ECB mode, which is not a problem as long as the nonces are unique. All right, then the rest is the template code used for standard encryption in Java. So once the nonce is encrypted, we get a unique IV. That becomes the IV for our regular AES encryption. Here is our regular AES encryption, which takes the data encryption key and the IV we just generated. But similarly, during decryption, although I put IV as another argument, you can imagine the situation that the decryptor just also does the same. In fact, the decryptor also generates the same get IV function. Of course, it has to generate the neck. Neck is the nonce encryption key, which is again derived from the same deck. Therefore, both the encryption and decryption will have the same nonce encryption key, and therefore the IV must be same. And hence, IV need not be sent from the sender to receiver at all, nor stored anywhere if you're talking about storing the IV in your disk, for example. Okay, so this technique is effective as long as the sender and receivers agree on how to exchange the nonces. Sometimes the sender can just put the message ID as part of the payload, and the message ID need not be secret, so it can be clear text. Of course, we are assuming here only confidentiality, no integrity in CBC mode anyways. So in that context, it's perfectly fine to use nonce-based IV. As you can see, there's a lot of extra work needed to get this up and running. In random IV-based situations, it's much easier. You just call a random number generator, a cryptographic random number generator to obtain the IV, and you call the encrypt and decrypt. Here, we take the message ID, we use the nonce encryption key to derive an IV from our message ID, or that message ID is nonce in our case. Okay, so that's basically it. Now let me run it for you and show you how the output looks like for the simple situation that the plain text messages are the same except the last bit. When you represent B in binary and C in binary, you will see only one bit is flipped. The least significant bit is flipped. Okay, so important things. First message, the nonce was 0, as I mentioned earlier. The second message, nonce, happened to be 1. Okay, now if you look at the IV, we derived this IV from this nonce. Remember, the IV was derived from nonce by encrypting using the key we derived from HKDF, right? The hash-based key derivation function. Okay, so what we got is the ciphertext corresponding to message BBB. Okay, now look at the ciphertext corresponding to another message. There's only one difference, right? The last bit is flipped, but the ciphertext has completely changed here. That's because of the fact that we encrypted this number nonce. Remember, the way encryption works is that usually AES behaves like a random function. If the input is a small difference from other input, you will have usually significant difference in the output. That's the reason our IV for the second message looks very different from the IV for the first message. Okay, remember, IV is derived from nonce. Okay, so as you can see, this technique is very effective if you wanted to avoid sending IV between the sender and the receiver, or store the IV anywhere on your disk. Okay, you have to be careful about the fact that nonce has to be used only once. Okay, so we can now summarize this problem and write a little algorithm to just a high-level algorithm idea. Okay. So if you want to avoid storing IV, what are the things you need to do? Of course, the sender and the receiver, or Alice and Bob in this case, must agree on the DEC. The data encryption key must be agreed, which is usually the key exchange algorithm will take care of coming up with the same key. That's not the scope of this talk. And then this is the step 0. I mean, you can't do anything without this, of course. Now comes the encryption side. During encryption, what do? We first have to derive the nonce encryption key, right? Nonce encryption key, which is constructed using the HKDF hash-based key derivation function on DEC. So meaning we applied to DEC basically. So we convert the DEC into a NEC in a simple terms. That's what we're doing here to obtain the NEC, which is the nonce encryption key. Once we have the nonce encryption key, now comes the question for each message ID in our in messages, right? In a list of messages, what do? We take our nonce as message ID, for example, and then we derive an IV. We derive an IV by encrypting. So we encrypt, right? Encryption could be whatever algorithm that's relevant. Encryption usually is AES in modern days. AES encryption. What is the key for the encryption? NEC is the key, right? And then we encrypt the nonce, so we get the IV. And now we go ahead and encrypt the data itself, right? So we get the ciphertext for the message 1 by doing encryption using the data encryption key, of course. And then we go to our message, right, of message ID. That means, I'm just talking about informally, syntax is not important. Okay, so bunch of messages we have, each message will be encrypted in this fashion. Of course, we get ciphertext. And now talk about decryption. Decryption actually should also construct the NEC, which will be the same NEC, of course, because we are applying to the same DEC. Remember, again, we are not sending, we're not necessarily sending the IV. That's the whole purpose of this nonce-based. If you want, you could still do that. There's nothing that stops you. If you want to send IV, then the receiver should not generate the IV again. Okay, so that's a protocol level collaboration, right? Okay, now for each message ID in the list of messages that he has to decrypt, of course, what he has to do is he has to again derive an IV, which is basically encryption of the NEC using the nonce, and then he takes get the plain text by doing a decryption using the data encryption key on the ciphertext for each. Okay, you don't have messages yet, of course. For each message in the ciphertext space, right? List of ciphertext. Okay, so you take the ciphertext of your message ID. So okay, well, you can say this is ciphertext. Okay, to be more precise, you have ciphertext of message ID that tells you you have the same thing here. All right, so you get plain text for each message ID. So the process is simple. You have a nonce, you derive a neck. Of course, you have to derive neck only once. You can reuse neck many times. You take the nonce, you encrypt the nonce, construct IV, and then regular encryption decryption process. Okay, so that's basically how you do nonce-based IV generation. What are the important things to note? Note very important things. Let me recall again. Never, nonce must be unique, need not be secret. Yes, secret. It's okay. It is okay if it is predictable. Okay, we actually make the IV unpredictable because we derive an IV from encryption process. Therefore, it's unpredictable. Okay. Anyway, this is the most important thing I want to tell you: how to generate IVs based on nonce. Thank you very much. That's all.